Okay, so this is Physical Metallurgy Lecture 2. So today is 20th of June, and so let's get started. So last week we did isomorphous phase transformations, and okay, we're getting a feedback. Pardon? Okay, so last week we did isomorphous phase transformations. So, and today we'll do eutectic alloy systems. But let me just recap what we did last week on isomorphous phase transformations. So let's go back to our example we had last week. So we had a phase diagram which was let's see, on this axis I had nickel, and here we have copper, and this, as we know, is temperature. So this is 100% nickel, and this is 100% copper, and this axis is weight percent copper. So this is our phase diagram template. And we know nickel melts at 1455 degrees centigrade. So above this, we have liquid. Below this, we have a phase, let's say alpha. And we know copper melts at 1085 C. And so we have a solid phase alpha below this, liquid above that, right? So the phase diagram is isomorphous, so it has this kind of topology. So we have liquid here, we have liquid plus a solid alpha, and we have solid alpha over here. So I just need to remind the audience that this is an equilibrium phase diagram. So equilibrium is a key word. And what do we mean by equilibrium? So what we mean is this, that suppose we take this composition and we are cooling down. So at this point we have liquid. In fact, we have liquid till here, and beyond below the liquidus. So this line is the liquidus, and below this line we start getting solid. So maybe Larry can turn off the volume. We're getting feedback. So below, so when I draw this horizontal line, this means that this is the composition of the liquid just below the liquidus, and this is the composition of the solid that'll come out. So let's call that alpha 1. So if I were to cool down a little bit further, I draw another composition. This is alpha 2. So the first metal to come out will have composition alpha 1. So this is in a liquid matrix. So we have like a pot of liquid, and we're cooling it down. So the first material to come out will have composition alpha 1. The second material to come out will have composition alpha 2, and so on. Alpha 3. But we're dealing with equilibrium conditions. So what we are saying is, instead of this, so alpha is increasing in copper, right? So in other words, as we go in this direction, the copper percent is going up. But what we are saying is that since we're dealing with equilibrium conditions, this composition is homogeneous. So if you were at temperature T3, this whole thing will have a composition of alpha 3, which means there is diffusion going on over here. So this is not like a tree structure where the composition changes as you go from inside to outside. Because of diffusion, basically copper diffusing in from the liquid, that we're saying we're cooling so slowly that a solid has uniform composition. So we're cooling, slow cooling, so that our solid phase has uniform composition. So composition does not vary from here to there. So how do we get uniform composition? We get uniform composition by what we call diffusion. And we did this last week when we were discussing lithium-ion batteries. So diffusion is the motion of mass because of concentration gradient. So from here to there, we have concentration gradient. The copper concentration is changing, so is the nickel. So that is a driving force to make the composition uniform. So that's a big assumption we're making. So these are equilibrium diagrams. In reality, when you're cooling or heating, they're not quite under equilibrium conditions. Okay, so with that note, let me start today's lecture. Another thing in this class is if you have any questions, you should ask the questions, because I'm sure people offsite also have questions. Easier for us to ask questions over here, right? Okay, so Gary, can I move to this board? So I'm going to start talking about eutectic systems. And the one I just described, the copper-nickel system, that's a cupro-nickel alloy. So we use copper-nickels in some of our plumbing because it makes the copper strong. So all alloys are stronger than their base materials. So if you have nickel and copper, each might be soft, but you mix them up, you make an alloy, the alloy is stronger. So for eutectic systems, let's pick a very important eutectic alloy system that we use, and that will be silver copper. So as usual, this acts as composition. So this is silver 100%. This is copper 100%. So this axis is weight percent copper. We go from 0 to 100 for copper. Silver melting point is 962 C. So we will never discuss Fahrenheit from now on till we live. Only centigrade. Actually, smarter people than us discuss Kelvin. So when we get to a higher level of intellect, we'll start discussing Kelvin. But we are in the middle, so we discuss Celsius. And here we have copper, which is 1085. And you might argue that you saw a book that said 1083, 1084. It's amazing. Depending on the reference you see, you have different melting points of copper, nickel, iron. The people are still trying to figure these numbers out. So that's pretty okay, I think. So now, as usual, here is liquid and here is solid, right? Above the melting point. And for pure copper, this is liquid and this is our solid. So notice I wrote alpha over here, beta over here. I'm expecting different phases over here. And then there is another very important point, temperature, that is called the eutectic temperature. And for this alloy, it's 779. So 779 C. And we have, now let me complete the diagram before I describe it. So this is what the phase diagram looks like. So this is a simple eutectic phase diagram. this composition is 8.8. This is, so that's percent. This one is 92%, and this is 28.1%. So this completes the phase diagram. So let's discuss this phase diagram. So let me pick a nice composition, this one. So we call this the eutectic composition. Now this is very important for us right now, because this is also called BAG8. So B stands for braze, AG for silver, and 8 is just a number. So this is we also call this braze filler metal. Even though it's an alloy, we call it a metal. So I'm deviating somewhat from the phase diagram because I want to explain the significance of this composition. So we use this for brazing. So if you have, let's say, 2 pieces of copper, like so. So this one is copper, this one is copper, and you want to join them. And just to complete the drawing, the plan looks like this is the elevation. So when I was growing up, this is how we drew our prints. We had plans and elevation, and we had side view. But in this case, since I have a square piece of copper, the side view will be the same as the elevation, right? So we want to join this. So we want to put alloy over here, braze alloy, to join that by brazing. So then, just another sidebar, if you're talking about brazing, what is soldering? So what's the difference? And what are these two things? So brazing and soldering are very similar. So they have to do with joining pieces of metal such that the braze material, so the braze liquidus, that's, in our case, this temperature for this alloy, because this line is the liquidus, and this one too. So this is the liquidus point for this braze. So braze liquidus temperature should be less than the T melting point of the 2 alloys you're joining, say A and B. In this case, we are joining copper, right? So brazing is and soldering is where this metal you're using has a liquidus which is less than the melting point of the pieces you're joining. The difference between copper and brazing and soldering is that brazing temperature is above 450 C. The soldering temperature is less than 450 degrees C. So that's the sidebar. So let's discuss this composition. So what happens is, so if you were to be at this point, so we'll call this temperature X. At temperature X, let me apply the phase rule. So this is a phase rule. So phase rule says that P plus F is equal to C plus 2, but I'm keeping my pressure constant. So pressure is 1 atmosphere. So what this is the number of phases that are present. And this is number of degrees of freedom. This is number of components. Now, we are dealing with a binary system, so we have two components, AG and CU. So C is equal to 2 because we're dealing with binary system. Now, the number of phases here in this particular case is equal to 1 because just liquid, right? So that gives us F is equal to 2. So what does that mean? It means that degrees of freedom is 2. So at this point, I can change my composition and I still have liquid. I can go back and forth and I still have liquid. Or I can go vertical, which is I can change temperature and I still have liquid. So I have 2 degrees of freedom, 1, 2. So that's what that means. Now let me get to the eutectic temperature. So we'll call it TE for eutectic. So let me rub this off over here and see what happens at the eutectic temperature. So at TE, what do we get? So the number of phases P, I have 1, 2, 3. So on this line, actually on this point and on this line, I have 3 phases that are in equilibrium. Alpha with this composition, beta with this composition, and liquid with that composition. So number of phases is 3. So, and we have F for number of degrees of freedom, and the C stays at 2, so 2 plus 1 is equal to 3. So F is equal to 0. So at the eutectic point, I have 0 degrees of freedom. So what does that mean? So this, when I was a sophomore, was a big struggle for me to understand this. What is this degrees of freedom? So notice, if I change the temperature, I go up by 1 femto degrees centigrade, I get into the liquid phase. So now I only have 1 phase. If I go 1 femto degrees centigrade below, I get into alpha plus beta, I lost my liquid. So if I have to have 3 phases, I cannot change the temperature. Now what about composition? Can I change composition? Again, you can't. If I go a little bit below, then I only have alpha and beta of different composition. Liquid is gone. If I go above, it's only liquid. So even the composition cannot be changed. So this is the beta composition, liquid composition, alpha composition. So that's why you have F equal to 0. So temperature cannot be changed. Composition cannot be changed. So nothing can be changed. So this point is fixed. As long as pressure is 1 atmosphere. If you change pressure, then this point will drift. Yeah, this position of the point is a function of pressure. So as we cool down, we get to this point. Now we have at TE, we have alpha, beta, and liquid all in equilibrium. So they all can exist. All 3 can exist at this composition and this temperature. The alpha composition will be 8.8% copper. The beta composition will be 92% copper. And the liquid composition is 28.1. So now what happens if I drop the temperature to, let me remove this point. So I cool down further, I get to that temperature, Ty. So what happens at Ty? Again, I draw a horizontal line. At Ty, the composition of alpha will be alpha Y, composition of beta will be beta Y. See, the composition changed. As I cool down, the composition alpha went from here to there, beta went from here to there. Now you might ask, how much alpha do I have? How much beta do I have, right? So for that, we apply the lever rule. So what the lever rule says is, okay, so let's find out how much alpha we have. So alpha is silver rich, right? So amount of alpha, or the fraction of alpha, a fraction is better. So we're assuming alpha plus beta is equal to 1 if alpha and beta are a fraction, right? So a fraction of alpha will be this line, I'll call this B, and I'll call this line A. So alpha will be B over A plus B. So if this is large, then I have more alpha. In other words, as I move towards the left, I have more alpha. And as I move towards the right, I have less alpha. So, and of course, the fraction of beta is equal to A or A plus B. So this is the lever rule. So this composition is 28.1%. So let's approximate how much alpha we have. So B will be approximately 92 minus 28. So 92 minus 28. And A plus B is actually from 92 to 8.8, right? So 92 minus 8.8. So this is, if I have to do roughly, just ballpark 70%, right? Or 80%, something like that. It's a big number compared to beta. So there's more alpha than beta. So that's important because we are cooling this alloy down at lower temperature. We want to see what happens. So we know that liquid transforms to alpha plus beta. So the beta is copper rich. So because the volume of alpha is more than volume of beta, that's a big factor. What that does is the beta comes out as platelets. And so that's the beta. And the alpha is in between. So if you're looking at the microstructure on a microscope, you will see, so let me draw only a little bit. So you'll see platelets of beta, and the surrounding area is alpha. So this is alpha, and you have, actually, I should correct myself. The whole microstructure will have these platelets of beta. So this is what we call a eutectic structure. Eutectic microstructure. So eutectic microstructure is platelets of copper-rich, and I've drawn it red because the microscope, it looked reddish. It has copperish color, whereas the matrix, which is silver, will look like silvery color. So this is a eutectic structure. And this is a structure you see for bag 8. Okay, so now let's discuss what happens in this region. So let me rub this off, stay on the same board. So that region I've marked in red, so this would be region from 8.8% copper to 28.1% copper. So this is 28.1%, this is 8.8. What if I'm cooling in this composition range with this composition? So what happens here is you have liquid here, and then from the liquid comes out alpha, and then when you get to the eutectic temperature, at the eutectic, at our temperature eutectic, the liquid plus alpha goes to alpha plus beta. So the liquid plus alpha converts to alpha plus beta. So let's see what happens. So above the eutectic temperature, what we see, if we were to be able to see that in a microscope, would be alpha particles in a liquid. So as we come down from the liquidus to the eutectic, the amount of alpha is increasing. So how do we know the amount of alpha is increasing? So we know that from a lever rule, right? So let me draw some horizontal lines like this. So as we come down, see, the amount of solid is this line divided by the total line. And at this temperature is this line divided by the total line. So as we come down to the eutectic, towards the eutectic, the amount of alpha is increasing. So alpha grows, and we're assuming within the alpha, you have uniform composition. So because we're dealing with equilibrium cooling. So once we get to the eutectic temperature, now the liquid plus alpha will give you alpha plus beta. So whatever happens below the eutectic, you will get the eutectic structure. So all the liquid that is remaining, and the amount of liquid remaining at the eutectic is this line divided by the total line. So is this line divided by the line from here to there. So that's a fractional liquid. So all the liquid will give you a eutectic structure. So you'll see alpha, which is silver rich. So alpha is silver rich. And you'll see copper rich particles which are drawn in red. And this region is also silver rich. And this is also alpha. So you have alpha over here, you have alpha over here. It's the same phase, same composition. So in a way, I can just remove this. So I'm going to remove this feature. And of course, liquid is gone. So what we have is these regions. See, these regions look empty, but they are alpha phase. So this is alpha, this is alpha, this is alpha. And in between these red lines is also alpha. So alpha phase is the matrix of this structure. So basically, you have a sea of silver-rich phase, and you have where you only have silver-rich phase, and then you have areas where you have the eutectic. So this alpha is called the primary alpha because it came out of the liquid in this temperature range. And the alpha that comes out later is in the eutectic. So in other words, right here is alpha, right here is alpha. So they're two alphas, but they're the same composition. Any questions on this? So it turns out that silver is a ductile material. So you can shape it, you can roll it, you can beat it, you can hammer it, you can draw it. And being the matrix, this alloy, this eutectic composition, is a ductile material. You can draw into wire or sheet or whatever. Okay, so this region is also called the hypoeutectic region. So we're dealing with so this is hypoeutectic. So we're dealing with a eutectic system. Hypo means less than. So this is less than hypoeutectic in terms of composition. So then we have hypereutectic. So this region from the eutectic to this point 92% is called hypereutectic. So I can work over here. So let's deal with the hypereutectic region. So that's from 28.1% to 92% copper. So if we were to pick this composition, and so once we get beyond this point, we cool down here, we get beta plus liquid. So if I were to draw a microstructure, beta particles are coming out, and here we have liquid. So as we come down this path, the amount of beta increases. So let's see what happens at the eutectic temperature. The amount of, so we're interested in how much liquid is left. So at the eutectic, this is the beta composition, this is the liquid composition. So amount of liquid at temperature eutectic is equal to this dimension, this value, let's call it C over B. So this is C and that's B. So that's the amount of liquid. And this liquid solidifies into the eutectic. So coming down over here, the amount of alpha keeps increasing, liquid decreases. At the eutectic, you still have some liquid. And that liquid, which is remaining, will form the eutectic. And in this microstructure, this will be the eutectic that you will see. So I should draw this red, because this beta is copper rich. And this region in here is alpha, and these lines I've drawn, they are beta. So notice now that even on the hypereutectic side, the matrix is the silver rich alpha, and these particles are beta. So these particles, they will be red because they're copper rich, and then you'll have so they're in a matrix of silver, and the eutectic structure is also silver matrix and like platelets of beta. So when you look at this structure at low magnification, so right now I've drawn it at high mag. If you were to decrease the magnification, you'll see basically some particles of beta, and then you'll see another kind of structure. So you'll see this dark structure I've drawn is eutectic, and this is my beta. Now, so you see two features in the structure, because at low mag, you cannot resolve these lines. It just looks like a blackish mess. So you have different shades. So you have bright shade and a dark shade. So we have these two features. So they are called, let me write this down, the constituents of the microstructure. So these are constituents of the microstructure. So we also have components. So the word components is reserved for silver and copper. So this eutectic system has two components, silver and copper. And this microstructure has two features you can see, and we call them constituents. So we have to keep in mind what is a constituent and what is a component. And then, of course, if we take this microstructure, we expand it, we make it bigger, we realize that this darkish region is actually eutectic of silver and copper. Okay, great. So we have covered the eutectic and we covered this whole composition range. Except I didn't mention what happens when you cool down in this range from this temperature to that temperature. Notice the composition of the alpha is decreasing in copper, right? The copper content is decreasing in the alpha, and in the copper, the silver content is decreasing. So the beta phase is becoming rich in copper, the alpha phase is becoming rich in silver. So there will be diffusion of the copper and silver because the alpha phase is giving off copper, the beta phase is giving off silver. But you won't see much change in microstructure. You'll just see that the composition is changing a little bit. Okay, so now I want to deal just with this section. So for that, I think I'll mosey on down to this board over here. And Gary's awake, so we can move on to this board. Okay, so I want to deal with what I call the isomorphous section of the phase diagram, which is either the far left or the far right. So I'm back to isomorphous. So isomorphous region of the eutectic system. So that's a neat region, and I'll draw it in a magnified view. So this is 100% silver, this is percent copper, and we have 962C as the melting point of silver. So we have this structure. I'm drawing the phase diagram. Let me draw it big. This is eutectic at 28.1% copper. This one is 8.8% copper. So what if I chose a composition over here? So this is the isomorphous portion of this alloy system. Here we have liquid. Here we have liquid plus alpha. So when we come down below this temperature, the alpha is precipitating out, amount of alpha is increasing. At this point, it is all alpha. So it's all alpha in this range. But then notice what happens. When we get below this point, now we have alpha plus beta, right? So at these points, beta is coming out. So up to this temperature, we had, in the microstructure, all we see is alpha up to this temperature. When we cool below this, beta wants to come out. So beta can come out. Actually, I should have drawn red dots. So let me draw red, because a beta is copper rich. So in the alpha matrix, we'll get particles of beta that precipitate out from the alpha matrix, because this region is alpha plus beta. So these particles can cause what's called precipitation hardening. So the alloy can get hard because of these particles of beta. And when it comes to heat treating section, we'll discuss what is precipitation hardening. Similarly, on the right side, we have a region from 92% onwards. So if I complete the phase diagram, this is at 92% copper. So in this region, again, if we cool down, then up to this temperature, in this range, we have beta, and below that, we have alpha plus beta. So below this temperature, in the beta matrix, alpha will precipitate out, and you'll get precipitation hardening. So any questions at this point? I think I'm almost done with the basics of the binary system. So this is a good time to ask any questions. So far we discussed equilibrium conditions. But what if I take these structures and I beat them up? I hammer them, roll them, draw them, change the shape. The amount of alpha and beta will not change. Just the distribution will change. So the pictures won't look as pretty. If I draw it, they'll just stretch out. So if you pull it in this direction, this structure will look elongated. So you'll get everything is elongated. But the amounts of alpha and beta will not change. They'll stay the same. Of course, the alloy will get hard. Okay, so we are done with the eutectic structure. So now there is another eutectic, which is useful for us. So we have a few minutes remaining. So let's discuss another eutectic system. So far we discussed B cup 8, which we use for brazing. There is another alloy which we call BNI6. So again, the B stands for braze. The Ni, of course, stands for nickel. And the 6 is just a number. So this composition is, let's see, 11% phosphorus plus 89% nickel. So this is also eutectic alloy. So let's draw the phase diagram for this one. So this is 100% nickel, and the melting point of nickel is 1455 degrees C, right? And on this axis is percent phosphorus. We'll just call it percent P. The eutectic is at 870. So let's draw 870 degrees C line over here. And then we have, okay, so this one looks like this and on. And so maybe I should draw this correctly. This point is at 11%, and this is, I think, 14%. Okay, So this is what the microstructure, what the phase diagram looks like. And this composition is a BNI6 eutectic composition. So this is our braze filler metal we use. So the problem with this is, notice as we cool down up to this point we have liquid, and then below this point we have, I'll call it just nickel plus Ni3P. So this composition is Ni3P. So we have a pure nickel line, right? 100% nickel. And then we have vertical line that is Ni3P. So this Ni3P is what we call an intermetallic. Now, this phase diagram continues onwards, but we're really not interested in this portion of the diagram because we're not interested in 100% phosphorus, right? That's just will vaporize. So our interest is only in the left portion of this diagram. So this Ni3P is a chemical compound. It's fixed. It's 3 atoms of nickel and 1 atom of phosphorus that gives you this intermetallic. We just call it intermetallic. Or I can call it intermetallic phase. So when we cool down from the liquid, we get liquid plus nickel. On this side, we get liquid plus Ni3P. Okay, so at the eutectic, at T eutectic temperature, what is our amount of liquid at the eutectic temperature? So now we know the amount of liquid is 11 over 14, right? So, I'm sorry, the amount of Ni3P. So, actually just below TE. So just below TE, at this temperature, we have converted, so the liquid has gone to Ni plus Ni3P below the eutectic temperature, right? Right there. So we only have Ni plus Ni3P. So how much Ni3P do we have? We have this much divided by this much by the lever rule, right? So this is about, 80% in that ballpark. So Ni3P dominates the amount of material compared to the nickel. So when the eutectic forms, you look at the eutectic, it'll have regions of nickel. I'm just drawing nickel as this. And in between is Ni3P. So the matrix is Ni3P. So we have nickel, and nickel is ductile, but nickel is in islands. So we have islands of nickel in a matrix of Ni3P. So Ni3P is like glass. So Ni3P is like glass. So if you were to hammer this, this will shatter into particles. So this alloy, BNI6, you cannot roll or draw or do anything to it. So this alloy is available in the form of a cream which has metal particles in an organic carrier. So you buy Ni3,6 as a paste with metallic particles in organic carrier, whereas the BAG alloy, which is silver and copper, that you can hammer away, you can form into a wire, etc. You won't have any problem. So I think this would be a good time to stop, because next time I want to discuss copper phos, which is B cup 5. So in 2 weeks we'll come back. Or 2 weeks we won't have a class, because that'll be the 4th of July. So 4th of July is on a Tuesday. So in 3 weeks when you come back, we'll discuss B cup, which is a copper phos alloy. And that's also kind of a eutectic, not quite. So we'll discuss that. But next Tuesday, we'll talk about lithium-ion batteries. So with that, we'll call it a lecture. Thanks, guys. But no questions? Larry, no questions? Jake, no? No. Okay, going. See you guys. Ciao.